Well, all the advertisements were in Chinese, so that kind of limited the audience.
There's a lot of looking out on those two sheets. Most of it's pretty well labeled. I don't put the essential stuff on here.
Okay.
You need to check
That's all one part.
and then there's your
Cool.
equation sheet.
Alrighty.
All right. Thank
See
you.
All right, friends. We're going to take a look at a slightly different twist on what we were doing yesterday. So in the back right now, I've got a meter stick mounted to my rotary motion sensor, and I'll clear this out. The pivot is right here at the center of mass, okay, ish. So what's the net torque on this thing? Right, 0, yeah, it's not interested at all in changing its rotation because the torque's 0 because I'm supporting it right at the center of mass. So I'm gonna change that. I'm gonna relocate this to the 60 centimeter mark. Slowly, painfully slowly. And then, that through a little farther. Daniel, can you be a deer and come give that thing a slight push? Yeah. A little bit of a push inside. Perfect. It's a big push. See how it goes. I'm gonna change my grade of data collection actually. So I can make that all smooth. All right, chat with your neighbor. What do you notice? Sorry. Here's the remote control. Alright. Yeah, what do you notice here? Motion. Motion. Or did you say ocean? Okay, fair enough. It's hard to tell. Ocean. Okay. All right, we got some waves. What seems to be true of the waves? Looks like the ocean. Well in. Anything else you can pick out here about the waves? Cheers. Is it periodic? What's the period? Pretty much, right? Pretty much spot on 2 seconds because we got 8 seconds of data and you see 4 complete waveforms here. So 2 seconds of the period. Are the graphs identical? Relate them to each other. You've talked about graphs before, friends. Up top, we have angular position in radians versus time, and this is angular velocity in radians per second versus time. So see if you can find some relationships there.
It was going like that. But where it was measuring it from is going like that.
All right, so when this thing is at its minimum angular position, when it's at a minimum on the angular position graph, what's proof of the velocity? Slide down, yeah, you can see it's 0. When we're at our maximum positive angular position, slide down to the velocity graph, 0. Okay. So that whole like slope relationship we had earlier in the year seems to be in play. Very positive slope, that coincides with the most positive velocity. Very negative slope coincides with the most negative velocity. So they have that phase relationship. We talked about it a little bit yesterday with regard to a couple of equations. How the velocity is the derivative of the position function. So we're gonna hop back into some of that stuff here and see if we can't cobble together a way of analyzing this device. So this is called a physical pendulum. It's a little different than the simple pendulum where we just have a point mass or a bob out on the end of a very thin, low mass string. If you think about what's happening there, when Nathaniel displaces it to the side, that's the worst line I've ever drawn. All right. Oh, there we go. That's beautiful. The pivot is at the 0.6. I'm Frozen. Cheers. Just start singing songs from Frozen, and that'll clue me in. All right, so the pivot's at the 0.6 meter mark, and the center of mass is located here at the 0.5 meter mark. Okay, so the pivot kind of runs like that, and you've got a force acting at a distance from that pivot. That force is mg. And then previously we were describing this position vector, right? It originates at the pivot, it's drawn out to where the force acts. We were calling it R, but for purposes today, we're going to call it fancy L, okay? And then I'm also interested in this angle theta right here. So the reason when Nathaniel displaces that to the side, the reason it wants to swing back towards the center is there's a net torque on it due to its own gravitational force that it's experiencing. That torque would be mg L sine theta. So the bigger the angle, the bigger the torque. Right? Is that how that works? Run that by your neighbor really quick. We increase theta. That's going to result in the bigger torque there. I'm going to pop back over to our work from yesterday and these derivations that we came up with. Let's see. Grab all that jazz, bring it over to today. Oh, that's big. There we go. All right. And so one of the things that we picked up on yesterday was, well, we started out with position as a function of time and eventually landed on velocity as a function of time, acceleration as a function of time. But then if you look at that expression for acceleration as a function of time, it's negative omega squared a cosine omega t plus the initial angular position. Well, a cosine omega t plus the initial angular position is equal to x. So I could just come on down here to the acceleration expression and write acceleration as a function of position is omega squared x. Okay, that's linear, right? We've got linear acceleration, we've got linear position. I could turn that into angular by dividing those things by the radius. That would turn this into alpha, angular acceleration, and that would turn x into omega. And so then we need to look at, so we have this expression for angular acceleration, and I should come back up here. We can relate torque to the angular acceleration via the rotational version of Newton's second law here. Torque equals I alpha. Okay? So angular acceleration for both of those things. Let's talk about small angles for a second. Okay? Let's say I make theta 30 degrees. That would be what in terms of radians? Come on, West High mathletes. What'd you get? Pi over 6. What is that in real people numbers? 3.14 divided by 6? It's like a half-ish, right? 0.5, 3, 2, 1,
0.
something like that. Okay? Somewhere in that ballpark. Okay? That's the angle 30 degrees in radians. What about the sine of theta? What about sine of 30 degrees, I should say? So in other words, for angles less than 30 degrees, sine theta is really close to, I shouldn't say equals, I should say really close to the value of theta in radians, okay? 0.52 is pretty darn close to 0.50. Close enough for government work. That's called the skinny angle approximation. You probably didn't learn it in math class because precision, but this is physics, so 0.52, that's pretty darn close to 0.50, all right? Now, I point that out to you because what I'm going to do over here is I'm going to take torque and divide it by the moment of inertia, and that equals alpha. So in other words, mg L sine theta divided by I equals omega squared theta. And by the skinny by the skinny angle approximation, theta and sine theta are pretty close together for small angles. So I'm going to go ahead and cancel those things out. MGL over I equals omega squared. So if I take the square root of both sides, square root MGL over I. Good question. L is the position vector for the torque. It's measured from the pivot out to where the force is acting. So we were calling it R hat when we were dealing with torque, but in this realm, it's just fancy little L. MGL over I equals omega, and keep in mind that omega is 2 pi over big T. So if I divide both sides by 2 pi, I'm going to get 1 over 2 pi times root MGL over I is equal to 1 over T. And 1 over T is frequency, as we discussed the other day. If I flip everything, I'm going to have 2 pi root I over MGL. That equals the period. So let's take a look at that stick, and if we move the pivot, see if we can't predict what the period's going to end up being, okay? So let's take the stick again and put the pivot at 80 centimeters. The glare off your phone, off your glasses is distracting. Cheers. You can take them off, but I don't think you're going to be able to see your phone as well. The center of mass is at the 50 centimeter mark. Okay. So as I'm setting this up here, 2 pi root I over MGL. I know L is 80 minus 50 centimeters. I for this thing. I could use integration to figure out the moment of inertia for the stick about the 80 centimeter mark. But instead, this is when we talked earlier about the parallel axis theorem, this is a good opportunity to employ that. Okay? Because I know the moment of inertia of a stick about its center of mass, or at least I should, right? Check your neighbor really quick. Are they cool? What is the moment of inertia of a stick about its center of mass? Oh. Do you want fries with that? Just practice that. Do you want fries with that? That'll probably be more personal.
Y W W. What? It's an acronym.
All right. So stick about its center. What's the moment of inertia for that? Okay. Good for you. Anybody else? Not looking to get a foot in the door of the fast food industry? Nobody? Okay. Look it up. Sean's got a phone. You can find it, right? Okay. But anyways, if I know the moment of inertia about the center of mass, and I rotate it about some other axis that's distant from that, I can still use that. Okay, I can use the parallel axis theorem here to figure out what the effective moment of inertia is at the 80 centimeter mark.
Yep.
All right. So parallel axis theorem. So you're going to add the moment of inertia about the center of mass, which you said is 1/12 ml squared, plus then we're going to treat it as if all the mass is concentrated at the center of mass. And that's going to be located, well, this distance away, which is our little L. Different L, okay? But that's how we would find the moment of inertia for this thing. So 2 pi root 1/12 ml squared plus m other L squared. All that's over g ml. And so you can see the mass of the stick doesn't matter here. You can cancel that out. So give it a sniff. What should the period for this stick be? Okay, keep in mind, L is 1 and L is 0.3. right, let's give it a sniff back here. So then if you want to reach back to the remote control, give the stick a little pooch. What did we do to the period? Is it shorter? A little bit, right? It's got 1, 2, 3, 4, almost 5 complete waveforms there. Starts at an angular position of 0, and it returns to an angular position of 0 in about 1.55 seconds. That's enough. Ballpark. Over your head, 1.52, 3, okay. Yeah, we'll take that. That's more than 1 second. Okay, so that's why I kind of like this setup, because we're getting some insights into a physical pendulum, but it's also this is probably one of the more common applications of parallel axis theorem. Okay, so let me zip this out of here and try this one on for size. Okay, I stole this embroidery hoop from your grandma. Rude. It's just how I roll, bro. So I've got the pivot here at the edge of this thing, and this thing's got a diameter of, say, 0.26 meters. Okay? So I'll scratch that out up here for you.
Cube. So there's the pivot. Let's see where you land with that.
What's that? What's it? Oh, that's why I have for circle and
See if you can come to an agreement with your neighbors on a number value there. All right, Daniel, want to give it a pooch? A little trickier.
Never put anything back.
Right about 1.05-ish.
Yeah.
Okay. So, how we paralyze the center of that business? Yeah. So, it's a hoop. So that's MR squared. No. Yeah. MR squared. It's a hoop.
I'd be the same. Like a
Deep. So, the center of mass is right there. And so, let me get blue pen. This would be L. It would be 0.225 meters. And that would also equal the radius. So, forgot about the 2 pi. 2 pi root. For the moment of inertia, I'm going to have the moment of inertia about the center of mass, which would be mr squared. But again, r is L here. Plus, treating it as if all the mass was located at the center of mass. And the position vector for that would also be L. That's how far away that is from the pivot. So I've got that up top, and I'm dividing by mgl. So this is going to become 2 pi root. Oh, we'll cancel m out everywhere. I've got 2l squared over gl. So that L is going to get rid of that squared. So I'm effectively going to end up with 2 pi. 2 times L would be the diameter. So that's my 0.45 divided by G. 9.81. So if we throw that in the old Desmos, 2 pi root 0.45 divided by 9.81. Uh-oh. 1.345. What'd I do wrong? Did I screw something up in Desmos? 2 pi root 0.45 or 9.81. All right, Mother Nature back there says 1.05, but I'm getting 1.3 something. See if we can figure out where I ran astray.
Is length the radius or the diameter?
Length is the radius.
And use the diameter there.
I did. I have 2L, right?
Oh, you do have to know that? Yeah, you do.
And should I? When I'm finding the moment of...
Plus L and the thing for sphere is 1/2 mr squared, right? So then wouldn't it end up being 3/2 L squared?
Maybe. So I've got a hoop, right? And a hoop would be mr squared.
Oh, it's a hoop, right?
And then
For a disk.
this would be... The point particle version would be mr squared. So effectively, the moment of inertia for this thing is 2ml squared over mgl. Any insights, friends? What'd I do? Carson, what'd I do wrong here?
Huh?
Fix my math.
Want me to fix your math?
Yeah.
What's going on?
I got a hoop back there.
Uh-huh.
And every other period so far, when I've calculated the period, I've gotten it correct, and now I'm not. Now that I'm screencasting, which is always the best, right? Got the 2 pi. Yep. Got that. Yep. Oh, let's go back and look. What did I do last hour? Hoop. Oh, where did I get 0.45 from?
Yeah, diameter.
I did do the diameter. Eddie had me. I just wasn't listening. Thanks, Eddie. The diameter of the next thing is 0.45. The diameter of this thing is point. What? Whoa, bro. You guys let me write 0.45 up here?
Yeah. Pretty fun.
You guys are savages. That's 0.26. See, you're magic. I just need you around and everything's better.
All right. Just call
Thanks,
me out
buddy.
Baby Bio every day. And I'll send you-
Okay, can you come assassinate somebody for me?
Yeah. Who you want me to kill?
Oh, gosh.
Huh? They're not in here. They already left for the day. Huh? Stat test? I did better than I thought. Check that for Hughes.
Shh, shh.
Skipped a whole part on the
All right. There we go. I just wrote down the
That was
diameter.
me.
That's all.
I did that.
All right. Just your mere presence.
And
It's a gift. That's why it's called presence. All right. Now that he's dirt that one, let's go to the frisbee. And see if we can get some redemption here. By we, I mean me. All right. This is 0.45, in case you were wondering. So I'm going to put the pivot here. This is going to be oh gosh. So yeah, diameter 0.45. The pivot is going to be located 10 centimeters from the center mass. So not at the rim. All right. T frisbee. See where you land. right, then go ahead and give it a second douche. Alright, we're landing about 1.3 seconds. Ballpark. You'll know. So what's our geometry here? Is it a disc? It's a disc. All right. Redemption time. So 2 pi root. I'm going to have 1/2. Tripped over the first hurdle. 1/2 m r squared plus m times l squared. And that's over mgl. So mass will go away. And I'll get left with 2 pi root half of 0.225 squared plus 0.1 squared. That's over 9.8 times 0.1. Desmos. Uh, 1.3, 1.33. Take it. Ah, come on. All right, there you go. So those are kind of some of the main applications of physical pendulum parallel axis theorem. We'll talk a little bit tomorrow about torsion pendulums. That's shown up on the exam before. That's just like when you used to sit on the swing as a kid, kind of twist side to side like that. That would be happening. Did I screw something up here? Your pointed stuff? Ah, curses. What? This is 0.26. It should be 0.225. You let me spike the ball in the end zone and I hadn't crossed the goal line yet. There we go. Uh-oh. So much better. There we go. All right. So 1.2. We got 1.3 back there. That's probably why I like that other answer better, but this will work. We ended up with a period that was slightly longer. What might have caused that here? We've ever held a frisbee before. What? Oh, you did only say, can I throw it? You didn't say, throw it at the smartboard. So I guess you're okay there. All right, here you go. You ready? All right. So, what do you think, MC? What issues might we have with? Here, I'll just do this. What issues might we have with calling that a disc? So it's kind of a little bit of a compound shape. It's a disc with a little bit of a hoop to it on the outside, and it's probably a fair bit of the mass. If you want to pass around, you can kind of check that out. So there is a fair bit of mass, a mass. Yeah, let's not throw it. If you could just pass it to each other, that's probably safe. Okay.
Wow, it's frisbee.
Might have thrown us off smidgenly. Oh goodness. All right, cool. You got a little bit of time left if you want to hit up some mastering.